Welcome to today's session. In this video, we will tackle an exciting problem from LeetCode, problem number 1602, find nearest right node in binary tree. This problem challenges us to work with binary tree traversals and identify the nearest right node at the same level. Let's dive in and explore the approaches step by step. In this problem, we are tasked with finding the nearest right node of a given target node U in a binary tree. To clarify, we are looking for the first node that appears to the right of you at the same level of the tree during a left-to-right traversal. If no such node exists, we return null. A binary tree, by definition, is a tree structure where each node can have up to two children, referred to as the left and right child. The input to the problem includes the root of the binary tree and the target node U, both represented as tree node objects. The output is either the nearest right node to U or null if there isn't one. The definition of nearest right node is tied to the order in which nodes are processed at the same level, using a breadth-first traversal approach. Consider this first example. The binary tree is represented as 1, 2, 3, null, 4, 5, 6, and the target node U is 4. Looking at the structure of the tree, the root node 1 has two children, 2 and 3. Node 2 has one child, 4, and node 3 has two children, 5 and 6. The target node U, which is 4, is located at level 2 of the tree. At this level, the nodes are 4, 5, and 6, ordered from left to right. The node immediately to the right of 4 is 5, making 5 the answer. Therefore, the output for this example is 5. In this second example, the binary tree is represented as 1, 2, 3, null, 4, null, null, and the target node U is 2. The tree structure shows the root node 1 with two children, 2 and 3. Node 2 has one child, 4. The target node U, which is 2, is located at level 1 of the tree. At this level, the nodes are 2 and 3, ordered from left to right. The node immediately to the right of 2 is 3, so the output for this example is 3. Now let's look at the third example, where the binary tree contains only a single node, 1. The target node U is 1, which is also the root of the tree. Since there are no other nodes in the tree, there is no node to the right of you at level 0 or any other level. As a result, the output in this case is null. This example highlights the simplest possible scenario, where the tree consists of just one node and no neighboring nodes exist. There are a few important considerations and edge cases to keep in mind for this problem. First, in a single node tree, where the binary tree contains only the root node, the output will always be null, as there are no other nodes. Second, if the target node U is the last node at its level, the output will also be null, since no nodes exist to its right. Third, for deep trees with many levels but sparse nodes, a breadth-first traversal is necessary to ensure the correct level is processed. Finally, in a complete binary tree, where levels are fully filled, every node except the last one in its level will have a right neighbor. These edge cases emphasize the importance of understanding the tree structure and its traversal to accurately solve the problem. To solve the problem of finding the nearest right node in a binary tree, we first consider a brute force approach using level order traversal, or breadth-first search. The intuition here is straightforward. Since we are looking for the nearest right node at the same level, we process the tree level by level. As we traverse each level, we check if we encounter the target node U. If we do, we simply return the next node in the queue that belongs to the same level. If U happens to be the last node on that level, or if we don't find U at all, we return null. The time complexity for this approach is O(n), as we visit every node in the tree exactly once. The space complexity is O(w), where W is the maximum width of the tree, since that's the maximum number of nodes that could be stored in the queue at any time. While this approach is simple and handles edge cases well, such as when U is the last node in its level, it can be inefficient because we may continue processing nodes even after we've already found U in the current level, which isn't strictly necessary. Now, to improve on the brute force approach, we can optimize the level order traversal to stop processing as soon as the target node U is found. The idea remains the same. We use a queue to traverse the tree level by level. However, instead of continuing to process all nodes on a level even after locating U, we terminate early. As we add nodes to the queue, we include their level information, such as node level. When we find the node that matches U, we check the next node in the queue. If this next node exists and is on the same level, it is the nearest right node, and we return it. If the queue is empty or the next node is on a different level, we return null. This optimization still has a time complexity of O(n), as we only visit each node once, but it avoids unnecessary traversal beyond US level, making it more efficient. The space complexity remains O(w), where W is the maximum width of the tree. Overall, this approach is cleaner and faster, as it eliminates redundant work while maintaining the clarity of level order logic. An alternative strategy is to use a recursive depth-first search, or DFS. While DFS is typically used for depth-based problems, it can be adapted for level-based queries by carefully tracking additional information. In this approach, we maintain a dictionary that maps levels to the nodes at those levels. As we traverse the tree recursively, we keep track of the current level. When we encounter the target node U, we look up the dictionary to find the next node at the same level. If such a node exists, it is the nearest right node, otherwise, we return null. The time complexity of this approach is O(n), as we still visit every node in the tree. The space complexity is O(h), where h is the height of the tree, due to the recursive call stack. While this method works, it is less intuitive for a level-based problem and requires extra bookkeeping, such as managing the level dictionary. Compared to the BFS methods, this approach introduces more complexity without significant practical advantages, making it less suitable for this specific problem. After considering multiple strategies, the chosen approach is the optimized level order traversal. This method is well suited for the problem because it aligns naturally with the level-based structure of the task. By terminating early after finding the target node U, it avoids unnecessary processing, making it both efficient and straightforward to implement. Additionally, this approach handles edge cases gracefully, such as when U is the last node on its level or the only node in the tree. While BFS does require queue space proportional to the tree's maximum width, this trade-off is acceptable given the simplicity and clarity of the solution. On the other hand, the DFS approach, while more memory efficient in some scenarios, introduces unnecessary complexity and does not offer significant advantages for this problem. Overall, the optimized level order traversal strikes the right balance between efficiency and ease of understanding, making it the most practical and effective choice for finding the nearest right node in a binary tree. In this problem, we are tasked with finding the nearest right node to a given target node U in a binary tree. The key requirement is that this nearest right node must be on the same level as the target node. If no such node exists, we return null. To solve this, we utilize a breadth-first search, or BFS, approach, which allows us to traverse the tree level by level. To implement BFS, we start by initializing a queue. This queue will store tuples containing each node and its corresponding level in the tree, enabling us to keep track of which nodes are on the same level. We begin by enqueuing the root node at level 0. From there, we process the tree one level at a time. At each step, we dequeue a node from the front of the queue and check if it matches the target node U. If it does, we then look at the next node in the queue to determine if it is on the same level, as this would make it the nearest right node to U. If the node immediately following the target node in the queue exists and is on the same level, we return it as the nearest right node. However, if that next node is either not present or belongs to a different level, we return null since no right neighbor exists. After checking the target node, we continue the traversal by enqueuing the left and right children of the current node, along with their respective levels, into the queue. This ensures that we process all nodes systematically. Additionally, there are some edge cases to address. If the binary tree is empty, we return null immediately, as there are no nodes to process. Similarly, if the target node U is not found in the tree, the result is also null. These considerations ensure that the algorithm handles all possible scenarios effectively. The BFS traversal is particularly well suited for this problem because it guarantees that nodes are processed level by level, which is crucial for identifying neighbors on the same level. To implement this solution efficiently, we rely on specific data structures. The queue is fundamental to our BFS approach, as it provides a first-in, first-out mechanism to process nodes level by level. Each entry in the queue is a tuple containing the node and its level, allowing us to compare levels as we traverse the tree. This design ensures that we can determine the relative positions of nodes efficiently. In terms of complexity, the time complexity of this algorithm is O(n), where n is the total number of nodes in the tree. Each node is visited exactly once, enqueued and dequeued. The space complexity depends on the maximum width of the tree, represented as W. This corresponds to the largest number of nodes at any single level, as the queue must accommodate all nodes on that level at once during traversal. To illustrate, consider a binary tree structured so that the root has two children, and each child has two children of its own. This structure creates a tree with increasing width at each level, which the queue handles seamlessly during BFS. Now, let's walk through a concrete example to see how this algorithm works in practice. Imagine a binary tree where the root node is 1, with two children, 2 and 3. Each of these nodes has two children as well, forming the next level. Specifically, 2 has children 4 and 5, while 3 has children 6 and 7. The target node U is 5. We begin by initializing the queue with the root node at level 0. At the first level, we dequeue the root and enqueue its children, nodes 2 and 3, at level 1. Moving to level 1, we dequeue 2 and enqueue its children, nodes 4 and 5, at the next level. Then, we dequeue 3 and enqueue its children, nodes 6 and 7. At level 2, we dequeue 4 and then find our target node, 5. At this point, we check the next node in the queue, which is 6. Since 6 is on the same level as 5, we return it as the nearest right node. This step-by-step approach highlights how BFS efficiently identifies the nearest right neighbor while respecting the level constraints. Some important edge cases to consider include scenarios where the tree is empty, in which case we simply return null since there are no nodes to process. Another edge case is when the target node has no right neighbor. For example, if the target node is 7 in the tree from the earlier example, there is no node to its right on the same level, so we return null. Additionally, in a single node tree where the root is both the only node and the target node, there are no other nodes at the same level, so again, the result is null. In summary, this level order traversal approach is an intuitive and efficient way to solve the problem. By leveraging BFS, we ensure that nodes are systematically explored level by level, making it easy to identify the nearest right neighbor. The algorithm is robust, handling edge cases seamlessly and operating within optimal time and space complexity limits. This makes it a reliable solution for determining the nearest right node in a binary tree. Here, we start by importing the DEET class from the Collections module, which will help us implement a breadth-first search, or BFS, traversal. Within the solution class, we define the method findNearestRightNode that takes two parameters, the root of the binary tree and the target node U. The first condition checks if the root is null, and if so, we immediately return none, as there's no tree to traverse. Next, we initialize a queue for BFS. Each element in the queue is a tuple containing a node and its corresponding level in the tree. We start the queue with the root node at level 0. The while loop processes nodes level by level until the queue is empty. Inside the loop, we dequeue the first element, extracting the current node and its level. If the current node matches the target node U, we need to determine whether the next node in the queue exists on the same level. If it does, we return that node as it's the nearest right neighbor. If not, we return none, indicating there's no right neighbor on the same level. To continue the BFS, we check if the current node has left or right children. If they exist, we append them to the queue, incrementing their level by 1. This ensures that nodes are processed in level order. Finally, if the while loop completes without finding the target node U, we return none. This means either the node U is not present in the tree or it has no right neighbor. The method ensures that all edge cases are handled, including empty trees, single-node trees, and scenarios where U is the last node on its level. This implementation efficiently traverses the tree and uses the queue to maintain the correct level order, ensuring we can identify the nearest right node when it exists. To solve the problem of finding the nearest right node in a binary tree, we start by importing the necessary utilities and defining our solution class. Inside the findNearestRightNode method, the first thing we check is whether the root is null. If the root is null, there's no tree to traverse, so we immediately return null. Next, we initialize a queue to help us perform a breadth-first search, or BFS, where each element in the queue is a pair consisting of a tree node and its corresponding level. We add the root node to the queue, setting its level to 0. The BFS loop begins by polling the first element in the queue, which gives us the current node and its level. Here, we check if the current node matches the target node, U. If it does, we peek at the next node in the queue to see if it's at the same level. If the next node exists and its level matches the current level, we return it as the nearest right node. Otherwise, if there's no such node, we return null to indicate that no right node exists at the same level. To continue building the BFS logic, we now handle the traversal of child nodes. If the current node has a left child, we add it to the queue, incrementing the level by 1 to indicate that it's on the next level of the tree. Similarly, if the current node has a right child, we also add it to the queue with the increment level. This ensures that we process all nodes level by level, which is crucial for solving this problem. If the loop completes without finding the target node U in the tree, we return null at the end of the method to indicate that the node doesn't exist. Additionally, you'll notice that we've included a helper class, pair, to represent the combination of a tree node and its corresponding level. This is necessary because the Java standard library doesn't include a built-in pair class. The helper class is defined as a private static class within the solution, and its constructor accepts a key-value pair, which in our case is a tree node and an integer level. The pair class includes two getter methods, getKey and getValue, which allow us to retrieve the node and its associated level from the pair. These methods are essential for accessing the elements stored in the queue during our BFS traversal. Finally, at the bottom of the file, we define the treeNode class, which represents nodes in the binary tree. Each node has an integer value, as well as left and right child pointers, both of which are initially set to null. This class is a simple representation of the binary tree structure and is used throughout the method implementation. With this setup, our code is fully equipped to traverse the tree level by level, identify the target node, and return its nearest right node efficiently. Let's go through the first example, which involves a simple balanced binary tree. The target node is U equals 5. We start at the root node, which is 1, and initialize our queue with the root and its level as 1, 0. Next, we dequeue the root, 1. Since 1 is not equal to U, we enqueue its children, 2 and 3, with their levels increment to 1. At this point, our queue contains 2, 1, and 3, 1. We then dequeue 2. Again, since 2 is not U, we enqueue its children, 4 and 5, with their levels as 2. Now the queue becomes 3, 1, 4, 2, 5, 2. Next, we dequeue 3. Since 3 is not U, we enqueue its children, 6 and 7, both at level 2. The queue is now 4, 2, 5, 2, 6, 2, 7, 2. Finally, we dequeue 4. Since 4 is not U and has no children, we proceed to the next node in the queue. Now we dequeue the next node, which is 5, 2. This matches the target node U. To find the nearest right node, we peek at the next node in the queue, which is 6, 2. Since the level of this node matches the level of U, we return 6 as the nearest right node. In the second example, the target node is U equals 7, which is the last node in its level. The tree structure remains the same, and we repeat steps 1 through 4 from the previous example. At this point, the queue contains 4, 2, 5, 2, 6, 2, 7, 2. First, we dequeue 4, 2, and move on since it's not U. The queue now contains 5, 2, 6, 2, 7, 2. Next, we dequeue 5, 2, and continue for the same reason. The queue now holds 6, 2, 7, 2. We proceed to dequeue 6, 2. Since 6 is not the target node, we continue processing. The queue now contains only 7, 2. Finally, we dequeue 7, 2, which matches the target node U. However, when we peek at the next node in the queue, we find that the queue is empty. This means there is no node to the right of U at the same level. Therefore, the output is none. In the third example, we consider the simplest case, a single node tree, where the root node is also the target U. We start by initializing the queue with the root node as 1, 0. Dequeuing this node, we see that it matches U. Since there are no other nodes in the queue, the nearest right node does not exist, and we return none. To summarize the solution, we use breadth-first search, or BFS, to traverse the tree level by level. This ensures that nodes are processed in left-to-right order at each level. The queue plays a critical role here, storing tuples of nodes and their respective levels as node level. By preserving the level information, we can compare adjacent nodes as we traverse. When we encounter the target node U, we simply check the next node in the queue. If it exists and is on the same level, it is the nearest right node and is returned. Otherwise, if there is no such node or if U is the last node in its level, the output is none. This approach is both efficient and intuitive for solving the problem. The time complexity of this solution is O(n), where n represents the total number of nodes in the binary tree. This stems from the breadth-first search traversal of the tree. Here's why: in the worst-case scenario, the algorithm visits each node exactly once. Each node is dequeued, processed, and its children are enqueued, making the total workload proportional to the number of nodes. Now, since each enqueue and dequeue operation in the queue takes constant time, or O(1), the cumulative cost of these operations across all nodes is O(n). Although the algorithm stops as soon as the target node, U, is found and its nearest right neighbor is determined, the worst-case scenario is that U is the last node in the tree, requiring traversal of every single node. This is why the overall time complexity is O(n). The space complexity of the solution is O(w), where W is the maximum width of the binary tree. The width refers to the largest number of nodes at any single level of the tree, and in the worst case, this width can be proportional to n, the total number of nodes, such as in a complete binary tree. The space usage is primarily dominated by the queue used in the BFS traversal. At any given time, the queue holds all the nodes at the current level of the tree. For a complete binary tree, the last level might contain roughly n/2 nodes, leading to O(n) space usage. On the other hand, for skewed trees, where nodes are arranged in a straight line to the left or right, the queue size will not exceed O(1), as there's only one node per level. Considering best, average, and worst-case scenarios, in the best case, if the root itself is the target node U, both time and space complexity are O(1). For an average case, time complexity is O(n), with space complexity of O(w), because the traversal depends on the location of U and the queue size depends on the maximum width. In the worst case, with a complete binary tree, both time and space complexities are O(n). When comparing approaches, a naive method might involve traversing the tree entirely to locate U and then making another traversal to find its nearest right neighbor. This would result in a time complexity of O(n) for each traversal, leading to a total of O(2n), which simplifies to O(n). While the naive approach achieves the same time complexity as the BFS solution, it is less efficient operationally due to the need for two passes. The optimized BFS approach improves upon this by achieving the result in one traversal. Here's the mathematical reasoning behind the BFS approach. For time complexity, each of the n nodes is processed exactly once, dequeued and, if applicable, its children enqueued. Since enqueue and dequeue operations are O(1), the total time complexity is O(n). For space complexity, the size of the queue is proportional to the maximum number of nodes at any level, which is O(w). In the worst case, such as a complete binary tree, this width becomes O(n). For skewed trees, this reduces to O(1). This demonstrates that the BFS approach is both optimal and efficient in terms of time and space for solving this problem. When solving this problem, there are several common mistakes to watch out for. First, not differentiating levels during traversal can lead to errors. For example, if you're using BFS but fail to properly track when one level ends and another begins, nodes from different levels might get grouped together. A good practice is to use a queue with none markers or to maintain the size of the current queue to separate levels. Another mistake is confusing the nearest right node with any right node in the traversal order. It's important to ensure that you're comparing nodes at the same level, not just relying on their sequence in the queue. Additionally, some candidates overcomplicate things by using DFS, which requires manual tracking of levels and siblings. Due to the recursive nature of DFS, it's easy to mishandle the state and introduce bugs. Using inefficient data structures for BFS is another pitfall. For example, if you use an array and repeatedly pop the first element, it results in O(n) operations, which is inefficient. Instead, always use a queue for BFS. Finally, don't overlook edge cases. Scenarios like a single node tree, an empty tree, or when the target node is the last node in its level can trip you up if not handled carefully. Testing these scenarios is key to ensuring robustness in your solution. Now, let's discuss some insights that can help during interviews. A key pattern to recognize is that problems involving level-by-level traversal of a binary tree almost always require BFS. Identifying this early can save you time and mental effort. Additionally, if the problem constraints allow, you might explore a two-pass approach. In the first pass, you can assign level information to each node, and during the second pass, you can use that information to find the result. While this approach isn't always the most efficient, it can simplify your logic, making it easier to reason about. Clear communication with your interviewer is also crucial. For example, clarify assumptions such as whether the target node is guaranteed to exist or whether the tree might contain duplicate values. Finally, be prepared to discuss trade-offs between time and space complexity. BFS has an optimal time complexity of O(n), but the space overhead of the queue can also reach O(n) in the worst case. Understanding and articulating these trade-offs shows a strong grasp of the solution. There are also several related problems that share similar patterns, which can help you refine your understanding. For instance, LeetCode 116, populating next right pointers in each node, is a closely related problem where you connect all nodes at the same level. Similarly, LeetCode 102, binary tree level order traversal, focuses on the core BFS traversal pattern, which is essential for this type of problem. Another variation is LeetCode 117, populating next right pointers in each node 2, which tackles the same task as problem 116 but applies to binary trees that are not perfect. Finally, LeetCode 199, binary tree right-side view, involves level-based traversal as well, but its goal is to identify the rightmost node at each level. Exploring these problems will deepen your understanding of binary tree traversal and help you recognize reusable patterns across similar challenges. Lastly, let's examine some alternative approaches to solving this problem. The brute force method with BFS involves performing a level order traversal while maintaining a queue to track nodes at each level. Once you locate the target node, you simply return the next node in the queue for the same level. This approach is straightforward but requires careful bookkeeping to ensure levels are tracked correctly. Another option is using DFS with level tracking. Here, you pass the current level as a parameter in a recursive function and maintain a dictionary to track the last visited node at each level. This avoids the need for a queue but increases complexity and is more prone to bugs due to the manual state management required in recursion. Finally, there's the two-pass approach. In the first traversal, you annotate each node with its level, and in the second traversal, you use this information to find the target node's right sibling. This approach simplifies the logic and makes the solution more intuitive, but it comes at the cost of requiring two passes through the tree, making it less efficient overall. Each of these methods has its trade-offs, so selecting the right one depends on the problem constraints and your familiarity with the techniques. Great job following along. In summary, we used level order traversal with a queue to find the nearest right node in a binary tree. This approach ensures optimal time and space efficiency. Remember to practice queue-based traversal for similar problems. Thank you for watching, and don't forget to like, subscribe, and leave a comment if you enjoyed the video. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!